Welcome, class. Um, thus far in the course, we have studied about memory errors, ways to defend against some of these memory errors, as well as techniques for isolation and virtualization. So, today we are going to start a new module, um, and this module is going to be on authentication and protocols. In fact, this module that consists of both authentication protocols as well as capabilities and access control uh, has nothing to do with any individual vertical in computer security, but rather are the foundations that you will find applied over and over in many different verticals in computer security, um, be it cloud computing or mobile security or web security, IoT, whatever it is. So this is much more foundational stuff. So we will start the module today with some basics. So both authentication as well as the study of network protocols involves some knowledge of cryptography. Of course, our department has a variety of advanced courses on cryptography, and some of you may be taking this course this semester as well on cryptography. Nevertheless, I will not assume any background knowledge. And so today's lecture um, is going to be in two parts. So I'm going to have a separate part on the basics of cryptography. Those of you that are familiar with cryptography may feel free to skip this part. After essentially seeing what I'm going to be covering, I'll give you a very quick overview of what I'm going to be covering. And then you can directly skip over to the part on authentication as well as various primitives for authentication. Okay, so that will be the second part of the the uh, the lecture of November 25th. And then of course we'll have a separate lecture on network security protocols. Okay, so we will get started today by looking at some background information on cryptography. So I'm calling this a lightning primer on crypto. And the basic reason is because I'm not going to do any sort of justice to the topic of cryptography. The cryptography is an incredibly deep topic. Um, there is a lot of theory that goes behind cryptography, as well as the analysis of cryptographic constructs. We are not going to be doing any of that in this course. We are going to be rather clients of cryptography. So we will study cryptography from a black box perspective, right? So we will try to understand what the basic constructs are. Of course, sometimes we will need to delve into the details. For example, the details of RSA and so on, because we would like to build primitives on top of it. We would like to build systems on top of it. So, for example, if you need to understand how the transport layer security protocol or TLS, which used to be called SSL, works, you need to understand a little bit of crypto. And that's all network protocols, which is part of this course. So, let's do a very quick lightning primer on cryptography. As I said, those of you that are familiar with the basics of symmetric key cryptography, public key cryptography, as well as how RSA works, can feel free to skip this portion of the lecture. So normally I do this portion of the course on the blackboard or the whiteboard, but because we don't have the luxury of doing that now, I have written everything down and I have scanned it, and we will look at these in lieu of slides. Okay, so in cryptography, the basic entities, the basic actors are typically called Alice and Bob, right? Now, the setting is that Alice wants to send some sort of a message M to Bob, and Alice and Bob could be two different entities that are separated by the internet. So the message M must actually traverse the internet, which consists of all sorts of untrusted parties. We will call them Eve or Mallory, uh, very conveniently, because Eve is for eavesdropping and Mallory is for malicious actions. And this adversary can do all sorts of things. The adversary can try to compromise the confidentiality of him, right? And it can do this by observing the contents of the packets and trying to infer what message Alice sent to Bob. Okay, so if preserving confidentiality is the goal, Eve or Mallory can just try to read the packets and see and infer the contents of the message. Um, Eve or Mallory could try to compromise the integrity of him, which is that they could inject packets or modify the message as Alice is transmitting it to Bob. Um, Eve or Mallory could send a message to Bob pretending to be Alice and claiming to be Alice, but Bob will need to have some mechanism to determine who the message is coming from. Okay, and that is the topic of sender authentication. And supposing Bob has received a message from somebody claiming to be Alice, and in fact, Alice has sent the message, the topic of non repudiation essentially deals with the subject of how, even if Alice later on claims that she did not send the message, but in fact she did, then Bob can in fact prove that Alice must be lying. So that's non repudiation. Okay, so all of these are going to be possible with modern cryptography. And so, in order to see how this is accomplished, let's look at some of the basic constructs. Okay, so the basic construct in cryptography is this notion of an encryption function, which I will denote by this function E. It takes two parameters, right? It takes the plain text message M. This is the message that Alice wants to send to Bob. And it takes a key, which is nothing but a bit string. And it applies this encryption function to M parameterized by this key K. Okay, so it's nothing but K of M. So once you apply the key, the encryption function just takes one parameter, that's a plain text, and you get the cipher text. So all of these things generally work at the level of bits. So even if the message M consists of alphabets or numbers or things like that, you break it down to bits and you process it at that level. So that's the encryption algorithm or the cipher, uh, and C is called the cipher text. Now, uh, on the other side, what Bob does is that when Bob gets this ciphertext message C, oh, by the way, yeah, so if Alice wants to send the message M, she encrypts it and then she sends the ciphertext instead of the plain text. Okay, and when Bob gets the message C, he applies this algorithm D with some other key K prime. Could be the same key. We'll get to that shortly. That's the decryption algorithm. And the idea is that the decryption algorithm applied with this key K prime is supposed to reverse the effects of this encryption algorithm. So you get back M. Now, of course, once you do this, it means that when Alice sends something to Bob, what is sent over the network is this C rather than M. And the basis of all cryptography is to ensure that even if Eve or Mallory is able to see, uh, observe the value of this C, uh, they should not be able to infer M. And there are various notions of security. We're not going to get into that. Okay, there is something called chosen plain text attack based security, chosen ciphertext based attack security, and so on. These have popular acronyms: CPA secure, CCA secure, CCA2 secure, and so on. Right. So various crypto systems are proven secure against certain kind of attacker models, and based on that, they get a certification. Okay, so something like a CCA2 secure algorithm would be extremely desirable, and things like AES and RSA uh, satisfy those kinds of properties. These are the popular cryptographic algorithms. Okay, so as I said, there are various types of algos that are used for encryption and decryption. There are what are called stream ciphers. These generally treat the input as a message stream and then apply an algorithm to produce some ciphertext. And the popular example here is RC4. Uh, but we are going to be concerned primarily with block ciphers in this course. Uh, so examples are DES, AES, RSA, and so on. So block cipher is a kind of cipher algorithm that takes a message of arbitrary length, breaks the message into fixed size blocks, right? So it could be blocks of size 2048 bits. Okay, you could take the message, maybe it's a YouTube video, maybe it's a gigabyte long, doesn't matter. You will break it into chunks that are 2048 bits each and apply the encryption algorithm block by block. Okay, you'll get ciphertext also, and then all you'll do is you'll just uh, sort of concatenate the ciphertext of each one of the plain texts. Okay, so ciphertext will also be of fixed length. That's the idea. And if your message is not, let's say, a multiple of 2048 bits, you add some padding at the end. Okay, so we are mostly going to be concerned with block ciphers. Okay, and even within block ciphers, there are two types of ciphers: symmetric key ciphers and public key or asymmetric key ciphers. So let's start with symmetric key ciphers. Okay, um, so Alice and Bob, as I said, Alice, if she wants to send a message, she encrypts it with an algorithm. And if it's a symmetric key cipher, the key property is that the algorithm, the key that is used by the encryption algorithm is the same as the key that's used by the decryption algorithm. Okay, so the encryption and the decryption algorithm end up using the same key, um, and you know, uh, the decryption algorithm is just the inverse of the encryption algorithm when applied to the ciphertext, but it's the same key. Okay, so the most common example or the most popular example right now that's used in practice is AES, or the Advanced Encryption Standard. It's in extremely wide use. In fact, it is the layer on which, let's say, all of your packets are transmitted over TLS. Of course, there's a layer of RSA on top of it. We will see that in much more detail. But AES is the current standard. Okay. So these ciphers, I'm not really going to get into the details of how these are built. There is a handout that is posted, and you should look at it. But mostly, these symmetric key algorithms follow a structure called a Feistel cipher. Okay, so they do some permutations of the input, then they shuffle some bits around. They pass these strings to something called S boxes, and out comes some output. And they do this in multiple rounds. Um, so these are called substitution permutation networks or SP networks, and that's what a Feistel cipher is. You don't have to understand or examine them in any sort of deep detail for this course, but you should be familiar with their structure, right? A cryptography course will consider the structure of these Feistel ciphers in much more detail. But the idea is that these ciphers are generally designed via worldwide competitions. Right? AES was designed via worldwide competition by the US National Institute of Standards and Technology in the late 90s and the early 2000s. AES emerged as the worldwide champion in terms of ability to resist attacks and so on. And the key sizes here generally are around 512 to 2048 bits. That's generally um, the key sizes that are used. Okay, so that's symmetric key cryptography. The same key is used by Alice and Bob. Now, of course, there's a key problem. So if you share this 512 or 2048 bit key between Alice and Bob, you can use that in some sense to obtain more security, right? The message M can be arbitrary sized. It can be a YouTube video. It can be a file that's terabytes long, and you can still transmit it with this shared secret that's just 2048 bits. Of course, the question is, how do you get Alice and Bob to share these keys in the first place, right? They need to know the shared secret. They need to know this key K that beforehand before they're able to exchange any information. So how is this key given from Alice to Bob? Well, Alice can't just send the key K to Bob over the internet, because any adversary observing the connection between Alice and Bob will be able to infer that that's the key. You can't even try any clever trick. So, for example, you can't say, okay, Alice is going to transmit the first bit from here to Bob via, one routing via one path over the internet, the second bit via another path, and maybe these paths can be obscured from the adversary, and therefore that's how you hide the key. Those are all clever tricks, but those are all security through obscurity, and history has shown us that security through obscurity is no good. Okay, attackers are very clever. So That's the key problem with symmetric key cryptography, which is how do Alice and Bob establish this shared secret key K in the first place? Okay, so let's call this problem Q key because I'm going to be referring to it later, which is how do we even establish this shared secret in the first place? So that brings us to the next major flavor of cryptography, which is public key cryptography, as opposed to symmetric key cryptography. It's also called asymmetric key cryptography, but we'll call it public key crypto. Okay, so here the idea is that both Alice and Bob each have some public parameters. In other words, Alice has some public parameters that are known to everybody. In fact, she has to advertise them as broadly as possible. Maybe she can put it on her web page or her Facebook feed or whatever it is. Same thing with Bob. Okay. These public parameters can in fact be different, but in the first uh, version of public key crypto that we are going to be looking at, they're actually going to be the same for Alice and Bob. So in addition to this, Alice and Bob will also have some private parameters. So Alice will have her private parameter, Bob will have his private parameter. These are only going to be known to them. Okay, so Alice's private parameter will be only known to her, and she should not share it with anybody. Same thing with Bob. Okay, so and with this we are going to build a crypto system. So let me look at the first and the most basic form of public key cryptography. This is called Diffie-Hellman Key Exchange. It was actually invented by Whitfield Diffie and Martin Hellman in 1976, and they won the Turing Award a few years ago for that invention. Okay. By the way, they are also the founders of the field of public key cryptography. Even though it was realized for the first practical time as RSA, so RSA is also capable of doing what's called digital signatures that you can't do with basic Diffie-Hellman key exchange. But anyway, Diffie and Hellman are credited with the concept of public key cryptography. The fact that Alice and Bob can have public parameters and private parameters and still enable cryptography. Okay, so Diffie-Hellman key exchange essentially solves this Q key problem that is there on the top of the slide. So how can Alice and Bob create a secret that only they know, nobody else knows, and they should be able to establish this secret key K in this particular case, even though they have never met each other before. Okay, so it's not like Alice can write down this key K on a piece of paper and then send it over to Bob, or you know send it over an email or something like that, because those are all insecure ways. So I'm going to show you a secure way. Okay, and when I say secure, this is unlike symmetric key crypto. Most of public key crypto is based upon modern complexity theory. Okay, the fact that you know certain problems are hard to solve in the sense that we do not yet have efficient algorithms for them. So the Diffie-Hellman key exchange protocol is based upon the hardness of what is called the discrete log problem. Okay, so supposing we have a congruent to b to the power of x mod p, and so this is, if you have forgotten this notation, I suggest that you go back to your 12th standard textbook and then learn it. One number is congruent to another number mod p if the first number minus the second number is divisible by p. Okay, so in this case, a is said to be congruent to b to the power of x mod p if a minus b to the power of x is divisible by p. Okay, so let's say that a is congruent to p to the power of x mod p, and these have, you can talk about equivalence classes that are equivalent by the modulo relation and so on. But this is going to be the notation we are using. But anyway, supposing that a is congruent to b to the power of x mod p, we call this number x to be the discrete log of this number a to the base b mod p. Okay, so that's what a discrete log is. Just like a log, if a is equal to b to the power of x, you know that x is equal to log of a to the base b. The only difference here is that we are doing all of this reduced modulo p. Okay, in other words, divide by p and take the remainder. So that's called the discrete log, and it's known that uh, finding the discrete log is hard. In other words, if you're given a, b, and p all large enough, okay, it's computationally hard to find x. Okay, so when I say it's computationally hard, it is the best known algorithm is still exponential in the number of bits that are used to represent these numbers. Okay, when you're talking about number theoretic algorithms, you generally talk about it in terms of the sizes of the numbers expressed as bits. So, the it's all exponential in the number of bits used to express a, b, and p. Same thing for factorization, by the way, and that we are coming. Uh, Prime factorization is also similarly a hard problem. Okay, so that's discrete log. So now let's see how Diffie-Hellman builds on the hardness of discrete log. Okay, so here's the Diffie-Hellman Key Exchange protocol in one slide. So Alice and Bob have public parameters, which is in this particular case, two integers, G and P. Okay, so I have not listed down, there are certain assumptions that G and P should follow. G is in fact called the generator, P is supposed to be a prime number, and there's a certain relationship they should follow, uh, but I'm not listing them here. We'll just keep it simple. Okay, so Alice and Bob have this numbers G and P that are public, and in fact they are the same parameters for both Alice and Bob, as well as any other participant who wants to participate in this Diffie-Hellman key exchange. Now Alice has this uh, private portion of the key, which is A, okay, and Bob has a private portion called B. So A's portion is Alice's portion, which is A, is not known to Bob. Bob's portion B is not known to Alice. So here is how the protocol works. Okay, and I suggest that you all go become familiar with modular arithmetic as well as the properties of modular arithmetic. Um, and the properties, for example, if A is congruent to B mod P and C is congruent to D mod P, that in fact A times B is congruent to C times D mod P, and so on. Okay, so you should know all this. That stuff is basic 12th standard mathematics. I'm not really going to talk about it here. Anyway, so what Alice sends to Bob is G power A reduced mod P. In other words, Alice will take G, raise it to the power of A, divide that number by P, and set the remainder to Bob. That's what I'm showing over here, right? So G power A mod P. And Bob sends to Alice G power B mod P. Okay, G power A mod P can be computed by Alice, G power B mod P can be computed by Bob and sent to Alice. Now Alice on her part takes what Bob has given, okay, raises it to the power of A, and that actually turns out to be congruent to G power A B mod P. This is where you should go and review your 12th standard maths on on how things like exponentiation and so on work when you're doing it with modular arithmetic. But essentially, if you are able to take this number that Bob gave and then raise that to the power of A, that turns out to be congruent to G power AB mod P. That's what Alice does. Bob on his side takes whatever Alice has given, that's G power A mod P, raises it to B, that turns out to be G power congruent to G power AB mod P. And so what you can see is that Alice has sent this number to Bob, Bob has sent this number to Alice, and uh, those are all numbers that are visible to the adversary who is snooping on the connection between Alice and Bob. Yet Alice and Bob are able to construct G power AB mod P, which only they can compute. Right? You can convince yourself that any adversary who has access to both of these will not be able to compute this. You can multiply the two, that will give you G power A plus B mod P. You can try all sorts of things. You won't get G power AB mod P. The only way to get G power AB mod P is if the adversary can observe this and figure out the value of A, okay, which they can't because discrete log is not an easy problem. So given G bar A B mod P, G and P, can Bob identify what A should have been? The answer is they can't, because discrete log is a hard problem to solve. Same thing for G bar B mod P. So that's the basis of the security of the Diffie-Hellman Key Exchange. And you can see what's been accomplished. At the end of this, Alice and Bob have set up a shared secret, G bar AB mod P. And this shared secret can be used to bootstrap any sort of symmetric key crypto, right? So they can then use that key, G bar AB mod P, as this key K that they then use for any sort of further symmetric key cryptography. So that's Diffie-Hellman Key Exchange. It's the first and most basic form of public key cryptography. So public key cryptography is the first thing that happens. Then you establish this shared secret, and then you can exchange all further information using symmetric key cryptography. So symmetric key cryptography, I must mention, is actually very, very efficient. AES runs blazingly quick. In fact, there's hardware support for AES. There are co-processors and accelerators available to run your symmetric key algorithms extremely fast. That's not the case for things like public key crypto, which is still many orders of magnitude slower than symmetric key crypto. Hence, the preferred mode of communication for transmitting data in bulk is symmetric key crypto. So even TLS uses symmetric key crypto, uh, but of course they use a layer of public key crypto to establish this key K first. And I gave you one such example, right? How Diffie-Hellman Key Exchange can be used to establish this key K, subsequent to which you have a round of symmetric key crypto. Okay, so that's Diffie-Hellman Key Exchange. Uh, so now let's look at uh, RSA, which is the major public key cryptography algorithm. RSA stands for Rivest, Shamir, and Edelman, the founders of the RSA algorithm. Okay, and here the way it works is that Alice has a pair of keys, public key, which we'll call pub A, and a private key, which we'll call priv A. Bob has also got a public private key pair, pub B and priv B. Okay. The idea is the same as before, that Alice publishes widely this public key pub A, and she keeps this private key priv A private. It's only known to her. Bob likewise publishes this public key pub B widely and keeps this priv B private. By the way, I'm brushing a lot of things under the carpet. Publishing this public key widely is not that easy. In fact, there is a whole discipline behind it called public key infrastructure, or PKI, that goes behind the science of understanding how to distribute these keys and how to associate these keys with Alice. And we'll study a little bit of that. We'll study a concept called digital certificates and so on. But anyway, I mean, let's say that you can print this on your visiting card and give it to anybody that comes and visits you, or you can put it on your web page or things like that, right? That's how, let's say, we have public keys are distributed. So given public key cryptography, let us say that Alice wants to send a message to Bob, this message M, and she wants to preserve the confidentiality of this message M. The way that that would be accomplished is that when Alice sends the message to Bob, she will encrypt that message M with this public key of Bob. That's how the message is sent. So the ciphertext is nothing but the encryption function, which we have to yet understand how it works. We have to design such an encryption function, but it's applied to message M with the public key of Bob. Okay, so it's intended for Bob, so you encrypt the message with the public key of Bob. Now, Bob decrypts it by applying his private key. So the decryption algorithm, that's D. We have to yet design it, but uh, the private key is used to decrypt the message M. So D of priv B of E of pub B of M is supposed to yield back M. And that's the key thing. How do we design this D and D so that this is true? M equals to this number over here. But the security of this stems from the fact that no other entity can decrypt this content over here, this cipher text over here, because priv B is private to Bob. Okay, so it should be noted over here that only we are trying to protect confidentiality. Bob cannot yet determine who this message came from. Anybody can encrypt the message M and then send it to Bob, claiming it to be Alice. We don't protect against that in this method. If you want to also accomplish that, you can accomplish that using a method called digital signatures, and we are going to study this in much more detail now. But RSA also enables digital signatures, and we'll see that also. But later, okay, it's coming slightly later. Okay, so what we will do now is to understand the functioning of RSA. Okay, we will understand deeply how RSA works, and we will delve into the theorems that make it work. I won't be doing too many proofs here, and the reason is because I'm going to leave some of these proofs as homework exercises, but I will give you the sort of sketch of a proof. But one thing is clear: RSA is in fact a tour de force in applying elementary number theory to the problem of secure message transmission. So let us start with some of this basic number theory that we need. So the first one we'll start off with is something called Fermat's little theorem. Okay, here's the lemma. So supposing I take a prime number p, okay, and I take another integer a, which has the property that it is co-prime with p. Okay, GCD of a and p is 1. So then this theorem essentially claims that a to the power of p minus 1 is in fact congruent to 1 mod p. Okay, so if I take this number a, raise it to the power of p minus 1 divided by p, the remainder has got to be 1. So I'm telling you this because RSA is going to be based on a slightly more complex version of this theorem, which we are going to get to. But this is a fairly well-known theorem in basic number theory. And the proof is also actually not that hard. It is some simple combinatorial tricks and it just falls out. So here's the sketch of the proof. So let us say that I were to consider the numbers x1, x2, so on till xp minus 1, which are defined like this. So x1 is a mod p. Okay, so take the number a divided by p, take the remainder, that's x1. Okay, x2 is 2 times a mod p. Take the number 2a divided by p, what's the remainder? That's x2, and so on. Okay, so xp minus 1 is p minus 1 times a mod p. Okay, so the first observation, of course, is that because you're reducing everything mod p, all of these integers, right, and because a and p are co-prime with each other, all of these numbers should belong to this set 1, 2, 3, 4, so on till p minus 1. It cannot be greater than p because you're anyway reducing modulo p. And it cannot be 0 because they are co-prime. So it has got to be one of these numbers. In fact, I'll claim that this set of numbers x1 to x2 to xp minus 1 is in fact uniquely the set 1, 2, 3, 4, 5, 6, so on till p minus 1. So there are p minus 1 numbers here in x1 to xp minus 1. And if they are the same as this set, that means, this is nothing but a permutation of this set. Okay. So when can this set x1 so on till xp minus 1 not be the same as this set? The only case that can happen is if two of these numbers are equal. If two of these numbers are equal, then they will not form this full set of integers. Okay. So that's the argument for proving this claim. So if in fact this set is not the same as this set, then some two numbers here must be the same. So let's just call them xi and xj. What is xi? It's nothing but I times a reduced mod p, and xj is nothing but j times a reduced mod p. So that would yield that I times a is congruent to j times a mod p. And if I and j are less than p, uh, that's not possible because I and j are distinct uh, and they're co-prime. I minus j is co-prime to p, and a is also co-prime to p. So this cannot be possible. Okay. if you have a contradiction. So xi and xj cannot be equal. Every xi and xj are unique and they form this full set. Okay, so having established that, you can just take the product of these two sets. You multiply all of these numbers, right? That if you just multiply all of these, you get p minus 1 factorial, and you multiply the other way of representing all of them, x1 to xp minus 1, which is this. That's p minus 1 factorial times a to the power of p mod p, p minus 1 mod p. Okay. Now you have a common factor on both sides, right? Um, so when can you cancel common factors in modular arithmetic? You can cancel common factors if they are co-prime to this number. Okay. So p minus 1 factorial is co-prime to p. They are prime numbers, right? So by definition, all numbers below are co-prime to this. So you can just cancel it out. Okay. So you cancel it out, you get 1 is congruent to a power p minus 1 mod p, and that's what we wanted to prove. Okay. So that's Fermat's little theorem. Okay. So given that, now let's look at another concept, which is called Euler's totient function, or phi of n. Okay, so phi of n is in fact a number that counts something. So if I am given you an integer n, phi of n is the number of integers less than n that have GCD uh, uh, with n equal to 1. They are co-prime to n. The number of integers less than n that are co-prime to n. Okay, so what is phi of 6? Phi of 6 would be 2, right? What are the only numbers co-prime to 6? Well, it is 5 and 1, right? 2 is not co-prime, 3 is not co-prime, 4 is not co-prime. Okay, so the totient function counts the number of integers less than 6 that have GCD of 1 together with that integer. Okay, so you can easily convince yourself that the totient function of a prime number is the prime number minus 1. Here's another fact: if you're given two prime numbers p and q, not any two numbers, but two prime numbers p and q, the totient function of p times q is in fact p minus 1 times q minus 1. This only holds for a product of two primes, by the way. There is another formula for the product of three primes, more complicated, but we only care about this now. Okay, so now I'm going to tell you a slightly more complex version of Fermat's little theorem. The proof of this theorem is almost a mirror image of the proof of Fermat's little theorem, so I'm not going to prove it. Slightly more complex, but pretty much the same argument, that of establishing a relationship between two sets of numbers. But here is the sort of lemma that is a more general version of Fermat's little theorem. So supposing n is an integer and a is another integer, so that GCD of a and n is 1, then this theorem states that a to the power of v of n is congruent to 1 mod n. Okay, and you can see why Fermat's little theorem is a special case of this. If n was a prime, uh, then phi of n is nothing but p minus 1. Okay, but for a general integer, this is the relationship. A to the power of phi of n is congruent to 1 mod n. The proof is an exercise. Okay, so work it out. Okay, so given that theorem, that is this one right here. Okay, in fact, there is a corollary, a fairly simple corollary to this theorem. Again, I'll leave that proof as an exercise, which is the following. Okay, it states that if n is a product of two primes, p and q, and m is another integer that is less than this n, then for all integers x, if I take this integer m to the power of x times phi of n plus 1, that is in fact congruent to m mod n. Okay, so taking m to the power of x times phi of n plus 1, that is I multiply m to the power of x times phi of n, and I divide it by n. In fact, the remainder is m. So if you want to prove this, the starting point is this theorem right here. Okay. It's not too hard of an extension from here. You should do it as a homework. So prove this first and then prove the next theorem. So I'm not going to go over the proof. Okay. But we will take this theorem and then see how RSA works. I'll now teach you how the RSA algorithm works. So here is how RSA works. So in order to set up her public key and private key, Alice would do the following. Bob would also do the same thing. Everybody would do the same thing. Whoever wants to participate in RSA would do the same thing. Alice would choose two primes, P and Q. Okay. And these P and Q are supposed to be kept secret. Okay. So only Alice knows this. Same thing, Bob, right? He can choose some two other primes. Those primes should not be revealed. Nobody, Alice should not reveal these two primes. But anyway, she is only generating these two primes for some local computations. So given this P and Q, she computes phi of P times Q, which is of course P minus 1 times Q minus 1, as I told you earlier. Okay, and we'll use this term N to denote P times Q. That's fairly standard. Then what she does is that she chooses an integer E that is less than N, and in fact there's a relationship E and phi of N should actually, the GCD should be 1. Uh, and she finds another integer D such that E times D is congruent to 1 mod phi of N. In fact, it is guaranteed that such a D will exist when the relationship between E and phi of N is satisfied. GCD of E and phi of N is 1. Um, this integer D is guaranteed to exist. Okay, so she finds another D and then she releases this pair of integers E and N, which is this integer E, and this N, which is P times Q, as a public key, and D comma N is a private key. In fact, they are interchangeable. You can call one the public and the other the private, doesn't matter, but this is the standard notation. En is the public key, Dn is a private key. Okay, and this, so En is widely distributed to everybody and Dn is kept private. Okay, so the security of the scheme stems from the fact that factoring is a hard problem, computationally hard problem. So even if I were to give an adversary n, the adversary would not be able to easily compute p and q. Okay, so this is not like an integer n equal to 15 or something. Okay, this is a n is a massive integer. Typically the sizes of these integers are like 2048 bits, that large an integer. So these primes p and q are also of similar magnitude. Okay, so the best known factoring algorithm is exponential in the number of bits in n. So it is on the order of 2 power 2048, which is a massive number. It is more than the number of atoms in the known universe. So you can't easily break uh, n and then factor it to p and q by just seeing n. So an adversary who knows n cannot easily find p and q. So therefore, given En, the adversary cannot compute Dn, and that's how private keys are kept private. Okay, so that's the public key, private key. Now let's look at how encryption works. So let us say that Alice has got her public key pair, which is EANA. She's got a private key pair DANA, and likewise Bob has a public key pair EBNB, and he has a private key pair DBNB. So just recall that if Alice wants to send a message M confidentially to Bob, Alice does so by encrypting this message M with the public key of Bob. So in RSA, it's actually implemented like this: encryption of a message M under this public key of Bob is nothing but modular exponentiation of M to EB reduced modulo NB. Okay, so you should remember that RSA is a block cipher. So if M is an arbitrary long message, it is not processed like that. It is broken down into chunks. It is broken down into chunks or blocks, the length of each of which is less than the size of NB. So if NB is 2048 bits, M is also of similar size and it's less than NB. Okay, it's not the full message. So each chunk is encrypted as above, and the ciphertext is nothing but a concatenation of each one of these chunks. Okay, so the decryption algorithm is very similar. The decryption algorithm also involves modular exponentiation. So the it is implemented as taking the ciphertext C uh, and raising modular exponentiation to the power of dB, again reduce modulo NB. That's how you do decryption. So let's see why this all works out. Uh, so what is C to the power of dB mod NB? Well, C power dB. So C is what? C is, um, if you look at the previous slide, C was nothing but M power EB reduced modulo NB. So if you were to uh, use modular arithmetic, you'll see that this is nothing but M to the power of EB multiplied by DB, right? Raising it to the power all reduced modulo NB. So C power DB mod NB, that integer is congruent to M power EB multiplied by DB mod NB. But we know that EB times DB is chosen such that it's congruent to 1 mod phi of NB. Okay, that's how we chose E and D, right? We chose E and D so that they're congruent to 1 mod phi of N. So EB times DB is congruent to 1 mod phi of NB. What does that mean? It means that EB times DB minus 1 is a multiple of phi of NB. Sorry, this thing over here should be phi of NB, not NB. This thing over here is phi of NB. My mistake. Okay, so EB times DB is equal to X times phi of NB plus 1. Okay, uh, this is not NB, I'm sorry, this is phi of NB. And so if you were to look at the theorem, this corollary theorem, what does it say? It says that M to the power of an integer times phi of that number plus 1 is congruent to M mod N. And if you go and look at this again, this thing over here, it's my mistake. M to the power of X times this should be phi of NB plus 1 mod B. Right, that's what this is. M power EB times DB can be written as M to the power of X times phi of NB plus 1 mod NB. And by that corollary theorem, that's nothing but it's congruent to M mod NB. Now you know that M is processed in chunks. It's not the whole message. The chunks are each less than NB. So what is M reduced mod NB? It's nothing but M, because an integer is less than NB, so it yields back M. So you can see how applying the decryption function to the ciphertext again yields back the plain text. So that's how RSA works, right? That's the public key algorithm, RSA. So with that, I am going to conclude my uh, lightning tour of cryptography. Uh, I have left some proofs for you as homework. Please do them. And what we will do in the next part of this lecture is that we will take these basic constructs, symmetric key crypto, public key crypto, and so on, and build primitives on them. Okay, we'll try to obtain some of these guarantees like integrity, sender authentication, non-repudiation, and so on. Okay, all right. So that ends the portion of the primer for cryptography. So let me just stop recording.